So in the last class, we have dealt with fundamentals of collision or conservation of momentum, conservation of kinetic, and line of collision. So in this lecture, we will continue few more questions specifically that deals with collision. Okay, how the angles are preferred. Okay, how the kinetic energy is related with coefficient of restriction. So see this lecture and all the best. Now we study the concept of explosion. Okay, concept of explosion. So whenever a body, okay, of mass m and velocity v moving with velocity v suddenly explodes into some number of parts or some number of blocks m1, m2 and m3. m1 is moving with velocity v1, m2 is moving with velocity v2, m3 is moving with velocity v3. My question out here is, whenever explosion is happening, what are the equation that I can apply? See, if any ball, okay, is fitted with some explosive inside the ball, after explosion, okay, the forces exerted by the explosion on these balls are internal force, no? So if there are internal forces, that means the net external force on the system is equals to 0 before and after collision, isn't it? If I take the entire system as m1 plus m2 plus m3 as a system, there is no external force acting on the system. Okay, so if there is no external force acting on the system, the momentum of the system will always be conserved. So if the momentum of the system is conserved, I can always apply conservation of momentum. And the second equation that can apply is, see, this mass m1 plus m2 plus m3 will be equals to the original mass, no? After explosion, none of the masses will disappear or either get generated. Mass won't be generated or get disappeared, isn't it? So the net mass before collision is equals to net mass after collision. So conservation of mass. So whenever I have collision, I can apply two equations: conservation of momentum and conservation of mass. Okay. Now in this question, a shell that was moving with 500 meter per second. Okay. What happened? It exploded into three equal pieces. That means first mass, second mass, and third mass. That means the masses of all the three particles are same. Okay. M1 is moving with V1, M2 is moving with V2, and the third mass is moving with V3. Okay. So the initial total mass would be 3m, isn't it? Now the question is saying, if the kinetic energy, total kinetic energy of the system after collision is 1.5 times the initial kinetic energy, okay, what is the maximum value of V1? Okay, see, this explosion imparted some explosive energy into the kinetic energy of the particle, no? So some amount of the explosion energy or energy from the explosion was used to increase the kinetic energy of the particle or used to increase the kinetic energy of the system. I must find out the distribution of V1, V2 and V3 such that V1 is maximum, first condition. Second condition is the total kinetic energy of this system should be 1.5 times the kinetic energy of the initial shell. Okay, so let me first write down the equation of kinetic energy. Equation of kinetic energy. Okay, final kinetic energy half mv1 square plus half mv2 square plus half mv3 square. This is the final kinetic energy or total final kinetic energy. All the masses are equal. Should be n times, the value of n is given as 1.5. Should be n times the total initial kinetic energy. Total initial kinetic energy is nothing but half m, not m, 3m. Total initial mass 3m into v square, where v was the initial velocity, isn't it? Now see, I can cancel out the m part. Okay, I can cancel out half also out here. Okay, so this entire thing would become 3 nv square. So my equation of kinetic energy becomes v1 square plus v2 square plus v3 square is equals to 3 nv square. Now this equation of kinetic energy was itself given in the question, no? What else equation I can apply? I can apply the equation of conservation of momentum. Because there is no external force acting on the system, the initial momentum would be equals to the final momentum, isn't it? See, although some amount of explosive energies was used to increase the kinetic energy of the particle, the explosive was an internal force, no? Okay, so if this mass increase the velocity in this direction, equal and opposite increase would happen in this direction, isn't it? No external force is acting on the system. Okay, so there would be no change in momentum of the system. Okay, so if I apply conservation of momentum, total initial momentum, which is nothing but 3m into velocity v vector, is equals to total final momentum am v1 vector plus am v2 vector plus am v3 vector, isn't it? These are vector quantities. You can also write them in terms of I cap and j cap. Okay, but to simplify the process, I have just written in terms of vectors. Okay, these are vector additions. Now you can cancel out the m, isn't it? Then you'd get the equation as 3v square is equals to v1, sorry, 3v is equals to v1 plus v2 plus v3. Now see, I have these two equations that I made. Okay, and then I'll figure out the problem. So I'll write these two equations out here. So this was the kinetic energy equation, this was the momentum equation. Now I must maximize the value of v1. Okay, now check what's happening out here. Three vectors are there. Okay, three vectors are added. Fair and fine. How much the, or what is the angle between the vectors such that 3v is maximum? The vectors must be collinear, no? Okay, when collinear vectors are added, then only the resultant vector would be maximum. If the angle between vectors is nothing more than 0, okay, then the resultant vector would be less, isn't it? Only when the three vectors are collinear, then only 3v will be maximum, no? So I get the intuition from this equation that after explosion, all the velocities would be collinear with the initial velocity. Okay, to obtain the maximum values, suppose I want to obtain the maximum value of 3v. Okay, what must be the angle between v1, v2 and v3? They must be 0, no? So all three vectors must be along the same line. Then only when you add them, the resultant would be the maximum value, isn't it? So from this equation, I get the idea that the velocities are collinear. Okay, all the velocities lie in the same line. Now see, I have to maximize the value of v1, no, such that v1 plus v2 plus v3 is equals to 3v. So the resultant is fixed. Okay, this is 3v, such that now I have to obtain the maximum value of v1. Okay, v1 can itself be 3v, v2 and v3 can be 0, v1 can be more than 3v. Okay, v1 can be more than 3v, where v2 and v3 can be in opposite direction. Okay, and any other possibilities. Okay, to maximize the value of v1, okay, the most significant conclusion is v1 is very large. Okay, and v2 and v3 are acting in opposite direction, such that v1 vector plus v2 vector plus v3 vector is equals to 3v. Okay, v1 vector plus v2 vector plus v3 vector is equals to 3v. Okay, or this magnitude minus this magnitude minus this magnitude is equals to 3v. Okay, now the intelligent among you or the smart ones among you will say, sir, make this v1 very large. Okay, so and v2 also very large and v3 also very large. Okay, so v1 can keep on increasing, no? I can make it infinite as long as v2 is also infinite. Okay, fair and fine, you can do that, but my condition is being blocked by this equation. Okay, what I'm trying to say is, first let's see the situation what is happening out here. So that means after explosion, okay, instead of V1 going in this way, V2 going in this way, and V3 going in this way, V1 would be in this direction, V1, okay, V1 would be in this direction, say, whereas V2 and V3 would be in opposite direction, V2, V3, such that V2 plus V3 should be equals to, or V1 minus V2 minus V3 should be equals to 3V. Okay, so this is my condition of explosion. V1 is in forward direction, V2 and V3 are in backward direction. So you can do that. V1 is very large, V2 is very large in backward direction, V3 also is very large in backward direction. Obviously you can do that, but you're limited by this equation, or equation of kinetic energy. The equation of kinetic energy says that the kinetic energy, the final kinetic energy, is equals to 3n times initial kinetic energy. See, n times initial kinetic energy. That means what? V1 square plus V2 square plus V3 square should be equals to 3nV. Okay, see, this 3V is fixed, you cannot change this 3V. Okay, your idea was make V1 very large. If you make V1 very large, V1 square also would be very large. If V1 square is very large, can this equation be satisfied? No. Understood? So we are limited by this equation also. Understood? So you can make V1 like this, V2 like this, V3 like this, but you are limited by scalar equation of kinetic energy, such that V1 square plus V2 square plus V3 square is equals to 3nV. So somehow must optimize out here. See, V1 square plus V2 square plus V3 square is equals to 3nV. I must maximize the value of V1. Okay. So V2 square plus V3 square should be minimum, no? For V1 square to be maximum. See, in the equation of kinetic energy, everything is positive. Okay, all three values are positive. Now I say a square or x square plus y square plus z square is equals to some constant. Maximize the value of x square. So y square plus z square should be minimum, no? Then only x square should be maximum, could be maximum. So if v1 square plus v2 square plus v3 square is fixed, for v1 to be maximum, v2 plus v3 should be minimum, isn't it? Okay, understood? Now this equation was nothing but this one. See, direction of v1 is opposite to the direction of v2 and v3. Okay, so let's write this equation in algebraic terms. Algebraic term means 3v plus v3 plus v2 is equals to v1. Okay, so this equation when written in algebraic terms, that means when written in these terms, or if I take the magnitude only, okay, if I'm only calculating the magnitude or from the perspective of magnitude, not vector quantity, 3v plus v3 plus v2 is equals to how much? v1. This is nothing but algebraic. This is the vector equation, this is the algebraic equation, same thing. Okay, now I have two equation. Okay, v1, see, this is the momentum equation, algebraic form of momentum equation. This is the kinetic energy equation. Now we understood that we have to make this value, okay, we have to make v2 square plus v3 square minimum to make this v1 square maximum. This much is understood. Okay, now let's change this question from the question of physics to a question of mathematics. Okay, my question is, what must be the value of v2 square plus v3 square such that v2 plus v3 is equals to L, where L is a constant. Okay, this L is nothing but a constant length, which is 3v minus v1. This L is nothing but v2 plus v3 also. So for a moment, let's term this L as a constant. Okay, I'm fixing this length L. Okay, so my question or my mathematical question is, what must be the value of v2 square plus v3 square such that v2 plus v3 is some constant? Or I can even rewrite this question as, what must be the value of x square plus y square such that x plus y is equals to L? I simply wrote v2 as x, v3 as y. Okay, so how do we solve this kind of problem? See, v2 plus v3 is some constant, so I can easily say v2 is equals to L minus v3. From this equation, v2 is equals to L minus v3. Okay, v2 is equals to L minus v3. Now if I substitute the value of v2 out here,
See, f is a function and the function is given by v2 square plus v3 square. And I must find the minimum value of this function. I must find the minimum value of this function. Okay. So if I substitute v2 out here, what happens? L minus v3 square plus v3 square should be minimum, or this function should be minimum, isn't it? Where v2 is nothing but L minus v3. Now see what happens. If I draw a plot of this function, okay, on the y-axis I have drawn this function, on the x-axis we have v3. Whatever is the graph, okay, however the graph looks like, at a minimum value, what would happen? df by dv3 should be equals to 0. So if I differentiate this function with respect to v3 and make it equals to 0, then I can find out the minimum value of v3, no, or minimum value of f, or minimum condition at which the function is minimum, isn't it? So therefore df by dv3 is nothing but I have to differentiate this entire term, L minus v3 whole square plus v3 square, isn't it, divided by dv3. Now when I substitute this, or when I differentiate this, it is nothing but 2 into L minus v3 into minus 1 plus 2v3 is equals to 0. 2 will get cancelled, or I can rewrite this as v3 is equals to L minus v3, or 2v3 is equals to L, or v3 is equals to L by 2. So I can easily say that v3 is equals to this constant divided by 2. So the value of v2 is nothing also but L by 2. If v3 is half the length, v2 is also half the length, no? So I can easily say that for the condition for v2 square plus v3 square to be minimum, v3 should be equals to v2. v3 or magnitude of v3 should be equals to the magnitude of v2. Then only v2 square plus v3 square would be minimum. Understood?
But the magnitude of v3 is equals to v2. Okay, magnitude of v2 is equals to magnitude of v3. So every v3 out here I can substitute by v2. Okay, understood? Now you have two equation. Okay, and how many variables? Two variables. v1 and v2 are the only variables, no? V is given in the question and n is also given in the question. We have two equations and two variables. So this equation can be written as v1 square plus v2 square plus v2 square is nothing but 2v2 square is equals to 3nv square. This is nothing but the kinetic energy equation. And this equation, okay, can be written as 3v plus v2 is nothing but 2v2 is equals to v1. This one is the algebraic form of momentum equation. Okay, momentum. Okay, now from the momentum equation I can easily say, no, that v2 is equals to, or 2v2 is equals to v1 minus 3v. Okay, if I send that 2 to the right hand side, v2 is equals to v1 minus 3v divided by 2. Now can I substitute this v2 out here? I have to substitute this v2 out here. So if I substitute the value of v2 out here, it would be v1 square plus 2 into, what is the value of v2? v1 minus 3v divided by 2 whole square, v2 whole square, sorry, v2 square is equals to 3nv square. Okay, so when I solve this equation, I get the value of v1. So I'll just write this equation out here. Okay, up out here. Okay, I simply wrote this entire equation out here. See, I can write this term only, something like this, whole square by whole square, isn't it? 2 square is nothing but 4, and this 2 and this 2 would become 2. Now if I multiply the entire left hand side by 2 and right hand side by 2, what do I get? 2v1 square, this 2 and this 2 would get cancelled. 3 into 2 is nothing but 6. So my equation becomes 2v1 square plus v1 minus 3v whole square is equals to 6nv. Now check. Can I expand this as a minus b whole square? So if I expand this as a minus b whole square, it will become v1 square minus 2ab, or 3 into, so minus 6v v1 plus 3v whole square is nothing but 9v square. So if I expand this entire term as a minus b whole square, it will be this term. So I'll write 2v1 square out here and 6nv square out here. Okay, 2v1 square is written out here, 6nv square is written out here. Now see this equation. 2v1 square plus v1 square is nothing but 3v1 square. Now if I divide the entire equation by 3, what do I get? This by 3, this by 3, this by 3, and this by 3. 3 and 3 would get cancelled. 3 2s are 6, 3 3s are 9, and 3 2s are 6. Now if I send this 2nv square to the left hand side, it will become 3v square minus 2nv square, no, is equals to 0. I have just sent the 2nv square to the left hand side. Now in this equation, I have only one variable, that is v1. Okay, and this is nothing but a quadratic equation. So in this quadratic equation, if I solve for the value of v1, I get my answer. Okay, so out here in this quadratic equation, this is nothing but a, or the value of a is nothing but 1. The value of b is nothing but minus 2v, and the value of c is nothing but 3v square minus 2nv square. And the roots of quadratic equation is nothing but minus b plus minus b square minus 4ac by 2a, isn't it? B square minus 4ac by 2a. So if I substitute the values, v1 is equals to minus b, what's the value of b? Minus 2v, plus minus b square, or minus 2v whole square, minus 4, the value of a is 1, the value of c is nothing but 3v square minus 2 nv square. So 3v square minus 2 nv square divided by 2a, or 2 into 1. Okay, out here minus into minus is nothing but plus, so this would get converted to plus. Okay, out here 2v square or minus 2v whole square is nothing but 4v square. Okay, I can take 4 common from these two terms, isn't it? So I took 4 common from these two terms. I can even take v square common from these two terms. Okay, so if I take 4v square common from these two terms, you will left with 1 minus 3 minus 2n. And if I open the bracket, out here 1 minus 3, it would be plus 2n, isn't it? Okay, and 1 minus 3 is nothing but minus 2. So we're left with minus 2. Okay, so instead of writing minus 2 plus 2n, I'm just writing as 2n minus 2. Okay, now out here you can take 4v square outside the square root, no? So if you take 4v square outside the square root, it would become 2v, and 2v divided by 2, 2 and 2 would get cancelled out here, 2 and 2 would get cancelled out here. Okay, so we are left with v1 is equals to v plus minus v under root of 2n minus 2. Okay, you can take v common from both these equations. So this is our final value of velocity, or this is the maximum value of velocity 1. See, or this can be written as velocity 1 is equals to initial velocity into 1 plus minus under root of, I can take 2 common out here, so 2 into n minus 1. Okay, so maximum value of velocity v1 is equals to this entire value, isn't it? So in this root, apply one more common sense. Out here it should be plus or minus. Okay, it should be plus, because 1 minus this thing would be nothing but absurd or negative, isn't it? So out here it would be plus, because negative is infeasible, not infeasible, impractical solution. Okay, impractical means what? See, if you put n is equals to 1.5,
1.5 minus 1 is nothing but 0.5. 2 into 0.5 is nothing but 1. Root over 1 is nothing but 1 only. So 1 minus 1 is equals to 0. So maximum value of velocity v1 is equals to 0 or what? No. So it should be 1 plus 2 into, so this negative is a impractical solution. Okay, so it should be 1 plus under root 2n minus 1. Now put the values. V1 is equals to, what is the value of V? 500, that is given in the question. Okay, into 1 plus under root of 2 into 1.5 minus 1, or V1 is equals to 500 into 2, which is equals to 1000 meter per second. Okay, so in this question, a particle of mass m moving with velocity v collides with another particle of same mass that was kept stationary. That means the velocity of this particle was 0. This was particle 1, this was particle 2. And the collision is head on. That means what? You get the intuition that the collision is 1D, isn't it? Head on collision. That means that striking this ball or this block strikes this block at the surface, isn't it? And after collision, what happened? Particle 1 moves with velocity v1 and particle 2 moves with velocity v2. Okay, in the question you have to find out the velocity v1 of particle 1. So what are the equations that we can apply in this question? If you think about it, we can always apply conservation of momentum, no, regardless of any type of collision. So equation 1 is conservation of momentum. The second equation is given itself in the question. See, as a result of the collision, the kinetic energy of the system decreased by 1%. That means what? The final kinetic energy is 1% less than the initial kinetic energy. That means what? Kinetic energy initial minus kinetic energy final by kinetic energy initial into 100 is equals to 1%. Okay, if I divide this, or 1 minus kinetic energy final by kinetic energy initial into 100, or if I divide this 100 out here, we'd get 1 by 100, no? So is equals to 1 by 100. 1 by 100 is nothing but 0.01. So 0.01. Okay, if I send this kinetic energy final to the right hand side and this 0.01 to the left hand side, we get something like kinetic energy final by kinetic energy initial would be equals to 1 minus 0.01. And what is 1 minus 0.01? 0.99. So 0.99. So we get that kinetic energy final is 0.99 times kinetic energy initial. So this equation was itself given in the question. Okay. So equation 2 is kinetic energy final is 0.99 times kinetic energy initial. Now let's apply conservation of momentum. Okay, conservation of momentum. What was the initial momentum? mv plus m into 0. So initial momentum is mv. What was the final momentum? Final momentum was equals to mv1 plus mv2. So mv1 plus mv2, isn't it? mv1 plus mv2. So you can cancel out the m out here and you would get v is equals to v1 plus v2. And this equation is found from conservation of momentum. So you get this equation from conservation of momentum. Now when you apply the energy of kinetic energy or equation of kinetic energy, okay, what is final kinetic energy? Half m v1 square plus half m v2 square, which should be equals to 0.99 times initial kinetic energy. What is the initial kinetic energy? Half mv square plus 0. So half mv square, isn't it? If I cancel out half m from left hand side and right hand side, I can easily get the equation v1 square plus v2 square is equals to 0.99 v square, or v1 square plus v2 square is equals to 0.99 v square. This is the equation of kinetic energy that is given in the question. Now I have two equations and two variables. Okay, The variables are v1 and v2. See, v is already given in the question. We have two equations, two variables, and we have to solve this one. So we can simply apply, what do we have to find out? We have to find out the value of v1, no? So to substitute v2 is equals to v minus v1, okay? And if we substitute this v2 out here, we would get something like v1 square plus v minus v1 square is equals to 0.99 v square, isn't it? And if I expand this term, a minus b whole square, a square minus 2ab plus v square. Okay, if I take the 0.99 v square from top and plus v1 square from top, so v1 square plus v1 square is equals to 2v1 square. So this would become 2v1 square. Okay, if I bring this 0.99 to the left hand side, it will become minus 0.99 v square, 0.99 v square. So this would become 0. Now v square minus 0.99 v square is nothing but 1 minus 0.99, which is nothing but 0.01 v square. So this minus this would become 0.01 v square. So plus 0.01 v square, 0.01 v square, isn't it? Now we have an equation 2v1 square minus 2v1 is plus 0.01 v square is equals to 0. Now what happens is we get a quadratic equation in the form of v1, and we know the root of quadratic equation is equals to minus b plus minus b square minus 4ac by 2a. So out here in this quadratic equation, the value of a is nothing but 2. 2 is the value of a, minus 2v is the value of b, and 0.01 v square is the value of c. So if you apply the roots of quadratic equation, v1 is equals to minus b minus 2v plus minus b square minus 4ac, or minus 2v whole square b square minus 4. What is the value of a? 2. What is the value of c? 0.01 v square divided by 2a, divided by 2 into, what is the value of a? 2, isn't it? Now if I square this, minus 2v whole square is nothing but 4v square. So this is nothing but 4v square. Now this 4v square, and you can take out common 4 and 4 from this equation, no? So if I take 4 common from both the equation, what do I get? 4. You can also take out v square common from both the parameters, v square and v square. So it becomes 4v square. So we are left with 1 minus how much? Let's eliminate this 4 and v square. 1 minus 2 into 0.01. And what is 2 into 0.01? 0.02. So 1 minus 0.02 into 4v square is equals to, means this value is equals to v1. What is the value of 1 minus 0.02? 0.98. 0.98. Okay, so we're left with how much? 4v square into 0.98. v square into 0.98. If I take this 4v square to outside, it will become 2v, no? So 2v out here, minus and minus becomes plus. We can cancel out the 2 from numerator and denominator, and we can take v common, okay, from both this term. Now under root of 0.98 is around 0.98 only, okay, because this number is very near to 1. So if I approximate under root of 0.98 as 0.98 only, see what is the square root of 1? 1 only. So under root of 0.98 will be very near to 0.98. Okay, it doesn't make a difference. So left with 1 plus 0.98 divided by 2 and 1 minus 0.98 divided by 2. So our answer would be v1 is either v into 1 plus 0.98 divided by 2, or v1 is equals to 1 minus 0.98 divided by 2 into v, isn't it? So 1 plus 0.98 is nothing but 1.98 divided by 2, and this becomes 1 minus 0.98. is nothing but 0.02 divided by 2 is nothing but 0.01. Okay, so the value of V is nothing but 10, that is given in the question. Okay, so V1 is either 0.99 into 10 or 9.9 meter per second, or 0.01 into 10 is nothing that 0.1, or V1 is equals to 0.1 meter per second. Now the question I have is, which one of them is the correct answer? 0.1 or 9.9 meter per second? See, if you add these two velocities, okay, 9.9 plus 0.1, this becomes tens, which was the initial velocity. See, that means addition of these two velocities becomes the conservation of momentum. Okay, so you can get the idea, one of these velocity or one of these velocities belongs to particle 2 and the other belongs to particle 1. Okay, we just have to figure out which one is which. Okay, if you see out here, n is equals to 1.0. okay, that means the kinetic energy decreased by 1%. So for elastic collision, how much is the decrease in kinetic energy? 0%, isn't it? Okay, so this collision is very much near to elastic collision. Okay, and for elastic collision, what would happen? If this particle and this particle collide, they would exchange their velocities. That means V1 would be very near to 0 and V2 would be very near to V. Okay, that means this velocity of 9.9 belongs to particle 2, which is very near to 10. Okay, and this velocity of V1 0.01 belongs to particle 1, which is very near to this particle or V1. See, in elastic collision, okay, whenever equal masses collide, they exchange their velocities, no? Okay, and for elastic collision, the loss in kinetic energy is 0%. So we can easily say that this type of collision is very much near to elastic collision, no? Okay, so when they exchange their velocities, this particle 1 will gain the velocity of 2 or be very near to the velocity of particle 2, and this particle 2 will be very near to the velocity of particle 1. So that is what I have assigned the values. Understood? See, I've always said, no, for elastic collision, the bodies will exchange their velocities if they're of equal masses. For inelastic collision, the bodies will stick together after collision. That's fair and fine. But you might ask, sir, what about if I have mass 1 with velocity v1 and mass 2 with velocity v2 and they collided? What about the velocities after the collision? Give me a generalized formula. Okay. So the generalized formula would be nothing but, see, if a body of mass m1 is moving with v1b or velocity of 1 before collision, collided with another particle mass m2 moving with velocity v2b. Now my main interest of the subject is, what are the velocities of mass 1 after collision v1a, and what are the velocities of mass m2 after collision v2a. Okay, they can be simply given by the formula v1a is equals to m1 v1b plus m2 v2b minus m1e into v2 minus v1 divided by m1 plus m2, and m2 is equals to, or v2a is equals to m1 v1b, same thing. And out here the only difference is, for v1a use m1 into e, for v2a use plus m2 into e. The remaining formula remains as same. Okay, now if you observe this formula, what is this? This is nothing but the total initial momentum, which is also fortunately equals to the total final momentum. So if I want to rewrite this formula, I can also rewrite this formula as total momentum minus m1 into velocity of approach divided by total mass is the velocity of 1 or body 1 after collision. Total momentum plus m2 into e into velocity of approach divided by total mass is the velocity of body 2 after collision. Now the first question is, where did I obtain this formula? How did I obtain this formula? I obtained this formula by using two equations. First one is the conservation of momentum and second one is the coefficient of restitution. So using these two equations, first one is the conservation of momentum and second one is the coefficient of restitution. If I substitute this value inside this equation, I get this formula. And from this formula, see, if you apply equal masses, okay, you can easily see that they'll exchange their velocities, fair and fine. If you apply coefficient of restitution is equals to 1, you can always see that the total momentum, you can easily see that they'll exchange their velocities. If you apply coefficient of restitution is equals to 0 out here, you can easily see that both v1a and v2a would have the same value, which is equals to total momentum divided by total mass. Understood? You can also apply this formula for 2D collision, provided you apply this formula along the line of collision. Okay, if you apply this same formula along the line of collision, you can also obtain the same result for 2D collision. Because 2D collision is what? 2D collision is nothing as same as 1D collision, isn't it? Along the line of collision, same formula as 1D collision, and perpendicular to the line of collision, no component of velocities changes. Okay, this question, what is happening is a particle of mass small m is moving with some velocity v. Okay, it collides with another particle of mass capital M, and this capital M was stationary. After collision, what happened? The particle small m, okay, got deflected by 90 degree. That means this was the initial angle of velocity, this was the final velocity of the small particle, and the angle it makes with initial velocity is 90 degree. And the particle capital M, okay, deviated by 30 degree from the horizontal. That means 30 degree from the initial velocity. Okay, this is v2, and this angle is 30. This is given in the question. That means particle M moved 90 degree to its initial velocity, and particle capital M, or the second particle, is deviated by angle 30 from the initial velocity. Fair and fine. The question is asking how much in percent and what has the kinetic energy of the system changed after the collision. If capital M by small m, if the mass ratio is 5.0. So this is a case of 2D collision, no? And whenever 2D collision occurs, what did I say? Always apply components along the line of collision and perpendicular to the line of collision. So first you need to determine the line of collision. Okay, so this is the final velocity v2, the initial velocity is 0. So delta v will be along this line, no? So delta v would be along this line, isn't it? So the line of collision is along this line. This is the line of collision. Right now, some of you might say, sir, why are you only taking mass 2? Why not take mass 1? See, even if you take mass 1, the answer or the line of collision would be the same. See, if you take mass 1, the initial velocity is in this direction. The final velocity is in this direction. What is delta v? Final velocity minus initial velocity. So delta v would be in this direction. So delta v is the line of collision, isn't it? Now tell me, this line and this line are the same thing, no? Okay, so it doesn't matter you take particle 1 or particle 2, the line of collision will be same. Now if I take the line of collision out here, the easier thing with particle 2 is, since the initial velocity of particle 2 is 0, we can easily figure out what the line of collision makes with the horizontal. Okay, so this is the line of collision, isn't it? This is the line of collision that makes 30 degree with the horizontal. Line of collision, line of collision. Okay, so this angle is 30, this angle is also 30. That means the line of collision makes 30 degree with the horizontal, isn't it? That is said in the question, or I figured that out. Now the first thing that you can apply is, whenever collision occurs, we can apply conservation of momentum, coefficient of restitution, isn't it? And if the collision is elastic, we can also apply conservation of kinetic energy. Fair and fine. So we'll apply conservation of momentum, okay, along the line of collision and perpendicular to the line of collision. Along the line of collision would be called as x-axis, and perpendicular to the line of collision would be called as y-axis. So conservation of momentum along x-axis, or along the line of collision, along the line of collision. So what is initial momentum? mv cos 30 plus 0 is equals to how much? Minus mv1. How much is this angle? If this angle is 30, this angle is also 30, and this entire angle is 90. So if this angle is 30, how much is this much? 90 minus 30, or is equals to 60. So this angle is 60. So initial momentum is nothing but mv cos 30 plus m into 0 is equals to mv1 cos 60 or minus mv1 cos 60. Okay, and what is the component of v2 along this line? Only v2 only. So plus m into capital V2. Now if I apply conservation of momentum along y-axis or perpendicular to the line of collision, okay, see, perpendicular to the line of collision, the velocity does not change for each particle. That means the component of, or perpendicular component of capital mass would be 0, perpendicular component of small mass would be v sin 30. Okay, so out here you can easily apply mv sin 30 is equals to plus 0 is equals to mv1. See, if along the line of collision is cos 60, perpendicular to the line of collision would be sin 60. So it would be mv1 sin 60. Okay, plus what is the perpendicular component of this velocity? 0, isn't it? So if we analyze this y component of equation, the m and m would get cancelled. Sin 30 is 1 by 2, sin 60 is root 3 by 2, isn't it? And 2 and 2 would get cancelled. So v1 is equals to how much? V by root 3. V by root 3. Now if I replace the value of v1 in the x component, I can easily get mv cos 30. Okay, v1 should be replaced by v by root 3. Cos 30, or sorry, cos 60 is nothing but 1 by 2. Okay, I need to find out the value of v2. Cos 30 is nothing but how much? Root 3 by 2, isn't it? So we get the equation mv root 3 by 2 is equals to minus mv by root 3 into 1 by 2 plus mv2. Now if I take this equation out here, I can send this term to the left hand side. It would become a plus mv by root 3 into 1 by 2, or we would have our equation such as this. Okay, now the thing to do out here is take mv common. If I take mv common, what will happen from these two terms? I took out mv common from these two terms, isn't it? And we get root 3 by 2 plus 1 by root 3 into 2. Now to add this one, the simplest thing would be to do out here is multiply this equation by root 3 by in the numerator and root 3 in the denominator. So we have a common denominator in both the equations. Okay, and if I take the LCM is same. So we'll get root 3 into root 3 plus 1. So we'll get this something like this, root 3 into 2 or root 3 into plus 1, and 3 into root 3 is nothing but 3. Okay, so 3 plus 1, 4 by 2 root 3, or if I eliminate this entire thing, would get 4 by 2 root 3, and 2 would get cancelled, so would get 2 by root 3. So our equation would become mv into 2 by root 3 is equals to mv2, or v2 is equals to mv2 by root 3 divided by capital M is equals to v2. I've just sent this capital M down out here. Now to find out how much in percent and in what way has the kinetic energy of the system changed after collision. So the question is basically telling us to find out kinetic energy final divided by kinetic energy initial. So what is kinetic energy final? Half m v1 square plus half capital M v2 square divided by what is kinetic energy initial? Half small m v square, and the larger mass has no initial velocity, so plus 0. So I can take out half common and cancel it out, no? Now let's substitute the values. V1 is equals to how much? V by root 3. So is equals to m into the value of V1 is nothing but V by root 3 whole square. See, V1 is equals to V by root 3 plus capital M. What is the value of V2? Small m by capital M into 2V by root 3. So small m by capital M into 2V by root 3 whole square divided by mv square. mv square. Now see, I can cancel out the v square and v square from out here, isn't it? 1 by root 3 whole square is nothing but 1 by 3. If I take small m by capital M whole square outside the bracket, it would be small m square by capital M square. And 2 square is 4, root 3 square is 3. So it would be 4 by 3 out here. Now I can easily cancel out the m and m square, isn't it? Okay, and I can take m common from these two terms. So it become how much? If I take m common from these two terms, it would become m into 1 by 3 into small m by capital M into 4 by 3, isn't it? Fair and fine. Now in the question it is given capital M by small m is equals to 5. So small m by capital M would be 1 by 5. Okay, 1 by 5. If capital M by small m, say out here, if capital M by small m is equals to 5, I can easily say that m by capital M is equals to 1 by 5, no? Okay, and this term becomes 5 3s are 15, 4 by 15, 4 by 15. Okay, if I multiply 3 by 5, 3 into 5, okay, 1 by 3 can be written as 5 by 15. And you have a common denominator. 5 plus 4 is nothing but 9. So this entire term becomes 9 by 15. 9 by 15. 9 by 15. Okay, m and m would get cancelled. So our answer is 9 by 15. So final kinetic energy divided by initial kinetic energy is nothing but 9 by 15, isn't it? 9 by 15. Or this can be written as 3 by 5. Okay, 9 by 15 can also be written as 3 by 5. So I can easily say that kinetic energy final by kinetic energy initial is equals to 3 by 5. So final kinetic energy is how much? 3 by 5 times initial kinetic energy, and 3 by 5 can be written as 0.6, isn't it? So final kinetic energy is 0.6 times initial kinetic energy. From this situation you can easily figure out that 40% of the energy is lost, no? That means if the final kinetic energy is 60% the initial kinetic energy, that means 40% of the kinetic energy is lost somewhere due to sound or due to deformation of the body or any other parameter or due to heat, isn't it? So this was our question. This question has nothing to do with collision but the concept of center of mass. In this question, the particle of mass m1 is moving up with v1 and another particle of mass m2 is moving rightward with velocity v2. We have to find out the momentum of each particle with respect to center of mass and the total kinetic energy of each particle of the two particles with reference to the center of mass. See, momentum and kinetic energy both are dependent upon velocities, and velocities is dependent upon frame of reference. So momentum and kinetic energy both are dependent upon frame of reference. Okay, so to find out the momentum and kinetic energy with reference to center of mass. So first we'll start with momentum or part A of the question. Okay, we have to find out what is the velocity of center of mass. Okay, velocity of center of mass. So x component of velocity of center of mass is nothing but how much? Mass of 1 into x component of velocity plus mass of 2 into x component of velocity divided by total mass, which should be equals to m2 v2 divided by m1 plus m2. and this is the x component of velocity of center of mass. Similarly, what is the y component? Y component of center of mass is equals to m1 into y component of velocity plus m2 into y component of this velocity divided by total mass. So y component of velocity is nothing but m1 v1 plus divided by m1 plus m2 j. So velocity of center of mass is nothing but I cap plus this j cap. Therefore, velocity of center of mass is nothing but this I cap plus this j cap. So this much is clear. This is the velocity of center of mass. Now you have to find out the momentum and kinetic energy with reference to this frame, with reference to a frame moving with this velocity. Okay. So we'll solve part A of the question. Momentum of particle m1. So momentum of particle m1 with respect to center of mass. So we'll divide this momentum of particle m1 with respect to center of mass in x component and y component. Okay. See, the question I have here is, what is the velocity of particle 1 with respect to center of mass in x component? It is nothing but velocity of particle m1 minus in x component minus velocity of center of mass. So what is velocity of particle 1 in x component? 0I minus velocity of center of mass, which is nothing but m2 v2 divided by m1 plus m2I. Similarly, what is the y component of velocity? v1. And what is the y component of velocity with respect to center of mass? v1 minus y component of velocity of center of mass. So if you take the LCM out here, it would be nothing but m1 v1 plus m2 v1 minus m1 v1 divided by m1 plus m2. m1 plus m2. What I'm doing out here is I'm taking the LCM as m1 plus m2. Then I'll multiply this entire parameter by v1. So we'll get m1 v1 plus m2 v1. And in this equation, I can cancel out m1 v1 and minus m1 v1. So m1 v1 minus m1 v1. So we'd be left with m2 v1 divided by m1 plus v1 j. Okay, this is the j component. So total momentum of particle m1 would be minus m2 v2 divided by m1 plus m2 I cap plus m2 v1 divided by m1 plus m2 j cap. So total momentum of particle m1 should be this value. And if you look carefully in this value, m2, m1 and m2, this entire thing is nothing but a scalar term, no? The only velocity vector, only terms with vectors are v2 and v1. So if I take the scalar term common out here, would be left with, if I take m2 by m1 plus m2, we are left with minus v2i plus v1j. Similarly, what is the total momentum of particle 2? Momentum of particle m2. We'll similarly divide them into x component and y component. Similarly, what is the x component of momentum of m2? It is nothing but v2 minus velocity of center of mass in x direction, and this entire thing is nothing but velocity with respect to center of mass in x direction. Now similarly, if I take the LCM out here, okay, and multiply v2 by m1 plus m2, what will happen? Would get something like m1 v2 plus m2 v2 minus m2 v2. So I can cancel out this m2 v2 and minus m2 v2, and we're left with m1 v2 divided by m1 plus m2, and the component of velocity is I. Okay. Similarly, y component. See, y component of velocity is nothing but 0 minus y component of velocity of center of mass. Should be nothing but 0 minus m1 v1 divided by m1 plus m2 into j component, which is nothing but minus m1 v1 divided by m1 plus m2. So total momentum of particle m2 with respect to center of mass is nothing but this velocity plus this velocity in j, this velocity in I plus this velocity in j. Now these are the m1, this m1 and m2 are the scalar component. So if I take m1 divided by m1 plus m2 as common, I'll get some m1 by m1 plus m2 into v2i minus v1j. That is the total momentum of particle m2. Okay. So I'll just keep the total momentum of particle m1 and total momentum of particle m2. Acha, I made a crucial mistake out here. If I am doing momentum, what is momentum? Momentum is nothing but mass into velocity, no? So this was nothing but the velocity with respect to center of mass. I have to multiply this entire parameter by mass of m1, then only it will become momentum of particle mass m1, no? So out here I have to multiply with m1. So entire thing I have to multiply by m1. Similarly out here, this entire thing was the relative velocity with respect to frame of reference fixed to the center of mass, isn't it? So I have to, for this is the velocity with respect to center of mass, no, particle 2. So in order to convert this to momentum, I have to multiply it by m2. So m2 out here and m2 out here. Okay. So this was the total momentum of particle m1 with respect to center of mass. This was the total momentum of particle 2 with respect to center of mass, isn't it? Now I'll just write down the velocities, this total momentum on the next page. Okay. So the total momentum of particle m1 and this was the total momentum of particle m2. Now if I want to find out the magnitude of the momentum, which is nothing but x component square plus y component square under root. So the magnitude of this momentum is nothing but, you can take this common, is nothing but m1 m2 divided by m1 plus m2 into minus v2 square or x component of velocity square plus y component of velocity square. Now minus v2 square is nothing but v2 square and v1 square is nothing but v1 square. Similarly, if I want to take out the magnitude of this momentum of particle m2, it is nothing but, we'll apply the same thing, or m1 m2 divided by m1 plus m2 under root of v2 square plus v1 square. Now you have to find out the total kinetic energy of the system. See, now some of you might have a confusion. Sir, I have a velocity and that velocity is nothing but vxi plus vyj. Okay. If you have to find out the kinetic energy of the system or of the particle from this information of velocity, which one of them is correct? Half mv square or half mvx square plus half mvy square? Which one of the velocities or which one of the following is correct for kinetic energy? What if I say both are equal? You can either find out the kinetic energy by the magnitude of velocity, or you can add up the x component of velocity and y component of kinetic energy. Sorry, x component of kinetic energy and y component of kinetic energy. See, if I simplify this, half m can be cancelled out from both sides. So v square is equals to vx square plus vy square, or v is equals to under root of vx square plus vy square, which is the same thing as the magnitude of velocity, isn't it? So it doesn't matter, you use the magnitude of velocity or you add up the x component of kinetic energy and y component of kinetic energy. Both will have the same value. Okay. So total kinetic energy of the system. Total kinetic energy of the system is nothing but momentum 1 square divided by 2 into mass 1 plus momentum 2 square divided by 2 into mass 2. Sir, we know the kinetic formula for kinetic energy is half mv square. How did you get this formula? Momentum square by 2m. See, kinetic energy can be written as half mv square, isn't it? Momentum can be written as mass into velocity. So what is momentum square? Mass square into velocity square, isn't it? So if you divide it by mass, is nothing but divided by mass. Okay. And if you multiply by 1 by 2, you can simply multiply by 1 by 2. Okay. So if I cancel out this mass and this mass, okay, so mv square by 2 or half mv square is nothing but kinetic energy, no? So p square by 2m is nothing but kinetic energy. So kinetic energy, or another formula for kinetic energy is also but p square by 2 into m. So I use this formula for kinetic energy out here. Understood? Because kinetic energy is equals to p square by 2m. Now what is p1 square? This whole value whole square. This is nothing but p1 square. P1 square divided by 2m1 divided by 2m1. Similarly, p2 square divided by 2m2 isn't it? This is the total kinetic energy of the system from the frame of reference of center of mass. Now I can write this as, or I can write this term as m1 m2 divided by m1 plus m2 whole square into under root of v1 plus v2 square. Similar thing I can do with this term also. Now see, under root of v2 square plus v1 square is nothing but we'll remove the square root, isn't it? And we'll remove the square root out here also. Okay, so this is our total kinetic energy. Now you can easily say that you can take v2 square plus v1 square common from both sides. Okay, so I'm taking v2 square plus v1 square common from both sides, and this entire term can be written as m1 m2 square divided by m1 plus m2 whole square. So similar kind of simplification can be done with this term m1 m2 square divided by m1 plus m2 whole square. Now m1 m2 whole square is nothing but m1 square plus, sorry, not plus, into m2 square, m2 square, and m1 and square root get cancelled, so we're left with m1 m2 square divided by 2. Similar kind of thing can be done out here. m1 m2 whole square is nothing but m1 square into m2 square, m2 square and square root get cancelled, so we're left with m2 m1 divided by 2. Now I can take out 2 into m1 plus m2 whole square common from both these terms, isn't it, and make it outside. And I can take m1 m2 common from both these terms, m1 m2, so we'll be left with m1 and m2 is taken common, m1 and m2 is taken common, so we're left with m2 plus m1 into m1 m2. Okay, so if I write this entire term little bit neatly, so this entire term would become this one. Now you can see that you can easily cancel out this one. Okay, the whole square would cancel out one of the terms, so we are left with the term total kinetic energy is nothing but m1 m2 v2 square plus v1 square divided by 2 m1 plus m2. And you know, specifically this term m1 m2 divided by m1 plus m2 is also coined as equivalent mass. Okay, therefore total kinetic energy of the system is equals to how much? m1 m2 divided by m1 plus m2, or equivalent mass, into half into v2 square plus v1 square.